on this subject. I'm going to actually grab the schedule here real quick. So this is going to span the next 2 weeks, and it's going to be a tough one because it's not necessarily difficult, but it is a new way of thinking about things that you already know, like shear and moment, internal forces and things like that. So we're going to be taking all that information that you already know how to find using statics, and we're going to repackage it into a new way to represent that information in the context of how those responses will change due to a moving load, all right? So we'll get more into that in a moment. But first, a couple of announcements, things to make sure I touch on. So Homework 7 solution will be released after the late deadline, which is tonight at midnight. So you'll have access to that to study over the weekend. We won't have that assignment graded and returned to you before the exam, but you'll at least have the solution to study from. And Homework 8, I posted that after last class. That will cover snow loads, rain loads, load combinations, and you're also going to be asked to read an article that focuses on the engineer who designed the World Trade Center Twin Towers, Leslie Robertson. So a couple years ago, he passed away, and the New York Times released a really nice article that just kind of discusses his life, but also focuses a lot on the famous project that famously failed, and the circumstances surrounding that. So don't wait until the last minute to start that. Through MSU Library, you all have free access to New York Times articles, right? So just make sure that you get access to that in time to complete the assignment. Every semester, there's always someone who waits until the very last minute and then says, I can't access the article. But no, you can. You need to log in and do the appropriate thing through the MSU library. So, all right, and then the exam, of course, is Monday, so don't forget about that. One final piece of advice as you prepare for the exam that I have is to make sure that you read the problem statements carefully, right? To avoid doing any unnecessary work. So, for example, on the homework that was due on Wednesday, right, I had several questions related to the wind loads problem, and folks thinking that the pressures that were provided were internal pressures. And I can see where the confusion came up, but in the problem statement, it was emphasized that those are net pressures, right? So they're not internal pressures. They were net pressures, and you had the case of positive internal pressure reported as well as the case of negative internal pressure reported, right? So just make sure that you read the problem statement carefully. Make sure you understand what's being presented, what you're being asked to provide, so you don't waste time doing unnecessary work. Because, for example, I might not ask you to do the entire process of seismic loads, all right? I might ask you to just do parts of it. So make sure you pay attention to that. All right, and then, so today, of course, we'll be focusing on a new topic, Introduction to Influence Lines. Before we dive into that, I did want to point out a few things. So related to the announcements that I just posted, here we have this. I just wanted to show you homework 8, all right? So the first 2 questions are related to snow loads, all right? The first one is focusing on a flat roof structure, and this is going to be the same building that you've been focusing on with the wind loads and the seismic loads problems in homework 7. So location in Anchorage, Alaska. And then the second question is focused on a sloped roof. And this is the one where you're going to kind of go through that whole process of calculating the sloped roof snow load and then breaking it down into the appropriate component for determining shear and moment. So you're going to be asked to draw the shear and moment diagrams for a typical rafter. And then the third question is focused on rain loads, or no, not really focused on rain loads. Rain loads are part of it, right? But it's focused on load combinations. So this is where, in the last lecture, I pointed out which load combinations in that list that you're going to be needing to use for this assignment. So part A is where you're going to be using those strength design combinations, the first 5 of them, all right? We don't have any earthquake loads in this list, so the last few combinations don't apply. And then for part B, or actually I should add to that, right? Not only do we not have seismic loads to consider, but we also are only considering the loads on the roof, right? We're not considering the lateral forces. So that's why, the other reason why you only need to focus on those first 5 combinations for part A. For part B, you're also going to be focused on a gravity load combination, but this time it's going to be an allowable stress design load, and specifically number 3. So this is part B is the one that's going to be closely related to that example that was at the end of the last lecture, where I said the first part of this example is worked out for you. The rest of it is, the solution is on D2L, so I encourage you to practice and go through it. You have to actually calculate the values for shear and moment diagrams and then overlay them to get the envelope, all right? And then here's the prompt for the New York Times article. Also in that assignment, I'm providing you with the design criteria that is specified by the local jurisdiction for question 1, all right? So for the structure in Anchorage, Alaska, you can see the relevant criteria is included here for snow, right? And then it's also interesting, since you've already addressed wind and seismic for this same structure, you can see the design criteria specified here as well for that, for the local jurisdiction. All right, so any questions on homework? Any questions on homework 7 that you all just submitted? Since we won't really have much of a chance to go over the solution before the exam, yeah?
When we were doing the wind base shear,
Mm-hmm.
and you were supposed to add up the individual loads at the diaphragm,
Yes.
how does that work? Because it said they were supposed to be equal, but if we're neglecting the 7.5 feet at the base, that doesn't include, and then we go into it the same way and include the base shear, or include that section when we multiply them over the area they act on?
So you were, the intent was to neglect the pressures tributary to the base in both approaches.
Okay.
Yeah,
Oh, okay.
yeah. Yeah, but yeah, you're right. If you, there would be different values if you didn't do that for one. But you should have gotten values that are, if you neglect the pressure tributary to the base in both cases, you should be seeing very, very close numbers, right? Rounding error, usually within about 1% is acceptable. So, yeah, they should have been very, very close. Yeah. Yeah. Any other questions?
Are these solutions posted tonight?
They'll be posted tonight, yeah. I'll set them to be automatically released right after the late deadline, which is midnight tonight. I checked and not everyone has submitted it yet, otherwise I would have gone ahead and posted it. So just to be fair, I'll wait until after the deadline has passed. Okay, any other questions? Okay. All right, so, right, there was one other thing for you that I have here, and just, yeah. All right, so I gotta switch over to a projector real quick to show you, or the doc cam, because I only have it on hard copy. Since we were talking about rain loads last time, and I couldn't find this piece of paper on Wednesday, but just wanted to show you. So this was a few years ago. You remember there were all those fires in Australia and then flooding in New Zealand at the same time, and it was right before COVID, and it was just, yeah, a whole storm of things. But this was when New Zealand actually experienced their 100-year flood, right? So they received 6.5 inches of rain in 3 hours. And so just with that, you can see the massive destruction that occurred. And I mean, this bridge, just is being torn apart by the force of that water. And then the whole neighborhoods are flooded. And of course, last summer there was the big flood of the Yellowstone River, and that's reported to be a 500-year flood. So you can still see the traces of the devastation from that, along the Yellowstone River. The high water marks on the bridges are, at least at the very minimum, locations where you can see trees lodged in the structure of the bridge and things like that. So it's just interesting to observe these events happening and understanding, what they represent. So I just wanted to point that out. All right. So now back to influence lines. Let's see. Here we go. All right. So, influence lines for structures. As I mentioned earlier, an influence line is a way to represent how internal forces or reactions at specific locations in a structure will change due to a moving load. So we're going to be looking at influence lines mainly for beams in this class. We'll also consider influence lines for frames if we have time. But you can also draw influence lines for trusses. And we're not going to focus on that in this class, but I'll mention briefly what that entails after we go through the basic introduction. So first of all, we can separate the influence line categories into determinate structures and indeterminate structures. With determinate structures, the influence lines will always consist of straight line segments, regardless of what type of response you're looking at. And also, regardless of how a true load is distributed, all right? So an influence line, and we'll get to this in a moment, it's always constructed based on a single point load acting downward that is, 1 unit in value, and it's moving along the length of the structure. So regardless of the type of response, again, you're going to have straight line segments representing your influence lines for determinate structures. Indeterminate structures will have mostly curved lines associated with them. And this is also tied to, and we'll talk more about this when we get to that point, but it's also tied to the fact that if a structure is stable, right, the deflected shape will consist of curved lines. So that's a little bit beyond what we need to think about immediately, but that's what it's tied to. So we'll come back to that. All right, so the lectures that are going to cover influence lines are now through lecture 31, which again, as I mentioned, will take us into the next couple of weeks. So our goal is to figure out how to construct and apply influence lines. And I've broken it down into 3 basic stages. The first stage is going to be covered in the first 2 to 3 lectures, which is going to focus on the introduction of influence lines and the basic construction, right? So we're going to define what the influence line is, use statics to construct the influence line, and then we'll show you how to identify key points for influence line construction to streamline that process and make it a little bit shorter. Then we'll apply those influence lines. So I'm going to show you, once you've constructed an influence line, you can actually use it for any load distribution, right? As long as it's vertical loads, You can use it for any load distribution. It doesn't matter if it's a uniform load, a increasing triangular load, right? A bunch of different point loads. You can use it for any different combination of vertical loads. And then the last stage is a different way to construct influence lines called the Mueller-Breslau principle. And this method is a lot faster to apply. It's a lot easier to apply, in my opinion. I think it might be a little bit confusing initially, but once you understand what the principle behind it and practice it a little bit, I think you'll appreciate it as well. So my warning here is don't rely on online resources for this topic, right? Because at this point, it will just be confusing. Most of the online resources will refer to the Mueller-Breslau principle. So once we get to that point, feel free, right? But at first, until we get there, try to avoid leaning on online resources to help understand this topic, right? You've got the textbook to refer to that will follow what I'm teaching. You have my lecture notes, right? Recorded lectures, examples that I'll provide. So focus on that, come to me with questions, avoid the internet for this topic at least until we get to the Mueller-Breslau principle, okay? All right, so in defining the influence line, right? So as I mentioned, we've got a unit load that is moving along the length of a structure, and the influence line will represent how that influences the response of the structure at a specific point. So the response, that could be a reaction, it could be internal moment, internal shear, internal axial force, it could be deflection. In this class, we're mainly going to be doing influence lines for reaction, moment, and shear. Actually, that's it. We're only going to be doing influence lines for reaction, moment, and shear. All right, so just kind of a side-by-side comparison between an influence line and an internal force diagram, right? So think about shear and moment diagrams over here. For that, you're drawing the diagram for a specific type of response, right? Either shear or moment or axial force, etc. For an influence line, you're drawing a line for a specific type of response and a specific type of load. In this case, a vertical load, right? It's really a vertical load that applies to an influence line. It gets a little bit different for trusses, but we're not going to deal with trusses in this class. So when you draw a shear or moment diagram, you can think of the loading as being fixed in place, right? You have a specific set of loads that you're drawing those shear and moment diagrams for. If the loads change, you have to draw a completely new set of shear and moment diagrams, right? For an influence line, what's fixed in place is the location of the response that you're drawing, that you're plotting, right? So you only need a new influence line if the configuration of the structure changes, if a support moves, or if a segment gets longer, or something like that. So as I mentioned before, right, once you have an influence line, it can apply to any different application of loads, okay? As long as it's a vertical load. So the variable for an internal force diagram would be the location of the response, right? You're plotting shear moment along the length of the beam. So for every point along that length, you have the response. For an influence line, the variable is the location of the unit load, right? So the location of the response is fixed in place. Your variable is the location of the point load. And so yeah, again, if the vertical loading changes for the influence line, you can still use it. For an internal force diagram, you're going to need a new diagram if the configuration changes or if the loading changes. All right, so conceptually, let's just think this through. You have a beam that is configured like this, right? A simple beam with an overhang. Then the process is to consider a traveling unit load, right? As it goes, we'll consider left to right. And what we're going to be focusing on are the reactions at A, the reactions at C, and the internal moments at B for different positions of that unit load. So think about the reaction at A first. When the unit load is located at A, right, directly over the support, what will be the reaction at A? Don't overthink it. One, exactly. When the reaction, or when the unit load is at C, what will the reaction at A be? 0. And what about when the unit load is at D? We without numbers to the span lengths, we won't be able to calculate an actual value for the reaction at A. But what can you tell about the reaction at A? Like, what do you know for sure?
Negative.
Yeah, it's going to be negative, exactly, because it's going to have to hold that end of the beam down when that unit load is placed on the free end. All right, so what about the reaction at C, right? If the unit load is at A, 0. If the unit load is at C, 1. And if the unit load is at D, what can we tell about it?
It's positive.
It's going to be positive. What else can we tell about it?
Greater than 1.
Very good. It's going to be greater than 1. All right, so does everybody see that? If the reaction at D, or excuse me, if the unit load is at D, right, we already determined that the reaction at A here would be negative, right? It's going to have to hold this end of the beam down. If the reaction at A is negative, and you have a unit load of 1 acting downward too, then the vertical reaction at C has to be greater than 1, right? Yeah, just summing forces in Y. All right, so now regarding the internal moment at B, all right, so now B is the fixed location for the influence line of moment at B. What can we tell about that when the unit load is at A? I think I heard the correct answer. Say it louder. 0, yes. Yeah, so if the unit load is directly over a support, so A or C, it's not going to cause any internal force at all within the beam, right? It's just going to go directly into that support. So at A and C, the moment at B will be 0. When the unit load is at B, what can we tell about it? It's not going to be 0, right? Can you tell if it's going to be positive or negative? Positive? Yep, that's correct. Right? It's going to be positive, and intuitively you can tell that if you place the unit load there, it's going to cause the beam to deflect like that, and you know that this curvature is a positive moment, right? And what about if the unit load is at D? What can we tell about the moment at B? Exactly, yeah, it's going to be negative. All right, so already conceptually you guys are rocking this, and these are the kinds of conceptual questions that you should use as gut checks for yourself as you go through these problems, right? And because it will get confusing, I promise you. It's, when I go through the lectures in class, you might be sitting there and thinking like, oh, this makes sense, it's so easy, this is boring and tedious, and yeah, it is kind of boring and tedious, but then you go and to apply it, and you might not be able to get very far because you're trying to figure it out. So that happens often, and it's common just because it's a new concept. All right, so another thing I wanted to point out, you'll notice the trend of how I'm writing these values out, right? So the value in brackets, or I guess I spelled it out here, right? So the value inside the brackets represents the position of the unit load, that's the variable. And then in front of that, I have the response. So the response should also include a notation that points out the location of that response, right? So the type of response and the location. And then, yeah, so that's going to be pretty consistent with how I'm going to present this topic throughout the next few weeks. All right, so if we plot those values that we determined, right, conceptually again, our influence lines for the reaction at A, reaction at C, and moment at B would look like this, right? So as we mentioned, right, for a reaction influence line, the value will be 1 at the location of the reaction's support, right? So for the location that is fixed for that influence line, that value will be 1 when the unit load is placed at that location, right? When the unit load is placed at a different support, the reaction influence line will be 0. For internal moment, and this also applies to internal shear, the value of the influence line will be 0 at any support, when the unit load is at any support, right? So this will always be true. And again, I'll just extend that last point to any internal response has an influence line value of 0 when the unit load is placed at a support. So here are some general rules to keep in mind as we go through this process, right? So each unit load placement represents essentially a different load case, right? So you can think about placing that unit load in a different location. You have to draw a different shear diagram, a different moment diagram. For a reaction influence line, the approach you want to take is to draw a free body diagram of the beam for each load case that you have, and solve for the reactions, right? And again, for a unit load, it's going to be pretty straightforward, pretty easy to do that. For internal shear or moment, first you want to identify the location of interest. That's the location that you're drawing the influence line response for. And you want to cut the beam at that location, right? So that's where you're going to expose the internal shear and internal moment. And then identify which reactions, if any, are present on each side of that cut. Once you've identified that, you can choose which side of the cut you want to use for calculating your responses, right? And you can use either one. You should get the same result no matter which side you use. Then you want to use statics to find the internal shear moment at that location. So we'll go through this in more detail later, right? For shear, you have to consider placing the unit load immediately before the cut and immediately after the cut. We'll get into that a little bit more later. For moment, you don't have to do that, but you do have to consider placing the unit load at the cut. So we'll go through that process. We probably won't get through all that today, but next week we'll see that a little bit more in depth. All right, so influence line application, right? So once we've talked about how to determine the influence lines, I'll show you how to apply them, right? So basically you're going to end up with, you've got an influence line for a response or a couple different responses that you're interested in, and you're going to take that and use it in conjunction with any kind of loading that might be applied to your structure. And so we'll show you how to do that. You can also apply it to distributed loads, and we'll look for that as well. All right, any questions? Okay. All right, so now we'll switch over to the skeleton notes. Start going through some examples and actually demonstrating how these influence lines will be applied. All right. So as I mentioned before, right, for a determinate structure, the influence line consists of straight line segments. And I meant to mention too, if you have a truss, and I'm actually going to go back to the slides real quick so you can see what I'm talking about. So a truss influence line is a little bit weird because you'll see if you look at it in the book, The influence lines are for a specific member's axial force, right? Because with trusses, you only deal with internal axial forces. You don't have shear and moment to think about, really. So you're taking a specific member and you're evaluating what its internal tension or compression will be for different panel loadings, right? So different panel point loadings. So you move the unit load from one joint to the next, and then you'll calculate, this is for CD, so calculate the internal force in CD, and then plot that value for each influence line, or for each unit load location. So that's what it would be for a truss. For beams, we're just going to be focusing on reactions, moment, and shear. All right, so we're going to take this beam, all right, so this is the same beam that we just conceptually investigated, but now we have numbers to apply to it. And we're just going to go through this process. So first, we want to place the unit load at A, all right? And then from statics, of course, we already talked about this conceptually. The reaction at A will be 1. The reaction at C will be 0. Next, place the unit load 10 feet to the right of the reaction at A. All right, by summing moments about C, we would find the reaction at A to be 0.67. And then by summing forces in Y, we would get the reaction at C to be 0.33. Then we would place the unit load at its next location, right? Same thing, summing moments and summing forces. We get the reaction at A of 0.33 and a reaction at C of 0.67. Continuing on, when the unit load is at C, the reaction at A is 0, the reaction at C is 1. So for those scenarios, right, and this is a very simple problem, but for those scenarios, you don't have to go through the statics calcs, right? Just, you can say by observation, since it's at a support, the response at the support is 1, the response at anywhere else is 0, right? When the unit load is at the free end, we get reaction at A is negative 0.33, and we get the reaction at C is 1.33. So now it may be helpful to summarize the values in a table. All right, so X represents the position of the unit load. So we've got 0, 10, 20, 30, and 40. We had the reaction at A was 1, 0.67, 0.33, 0, and negative 0.33. Reaction at C is 0, 0.33, 0.67, 1, and 1.33. All right, so plotting those values would look, let's see, we've got, is that 10 feet? We'll mark them like that. All right, we would end up with something like that for our influence line. The reaction at C I go for a shallower slope, so it's a little less encroaching on the next one. All right, something like that. So you can see the slope is continuous for these two reaction influence lines. And we'll talk more about those kinds of trends to look for, right, when you draw these as a check. Yeah. All right, so one thing I want to point out too, unlike shear and moment diagrams, it's not as essential for you to show that these influence lines will close at the end, right? They will naturally, right? So once you move the influence line off the beam, all responses are going to be 0, right? So that's just what that represents. But it's not as important to show that end closing as it is for shear and moment diagrams. All right, so sometimes, next we'll demonstrate the construction of shear and moment influence lines. And often, not always, but often you will need to use at least one reaction influence line in the construction of your shear and moment influence lines. So sometimes you might need to, even if you're not asked to find the reaction influence line for a problem, you might want to go ahead and find one of the reaction influence lines and use that information to determine your shear and moment. So, another point I wanted to make out, all right, so for shear and moment, we already talked about this in the presentation. It's important though, so I want to emphasize that you want to cut the beam at the location where the response value is desired. All right, and that is often, I'm going to be referring to that as the location or point of interest. All right, and also, when we go through this, keep in mind these sign conventions, all right, our standard mechanics sign convention for shear and moment. All right, so now we're going to look at shear. Shear and moment, really. All right, so for shear force, the one thing to keep in mind with that is that the influence line will be discontinuous at the specific point where the shear is desired. So at that location of interest, your value of the influence line is going to change right before that point and right after that point. So that's why we need to place the unit load at 2 locations at that area of interest. So you'll see that in this demonstration. So here, the same example, now we're going to be looking for the influence lines for shear and moment at B. All right, so B is our location of interest. And in order to do that, because B is in between A and C, we will absolutely need at least one of those reaction influence lines in order to figure this information out, right? So just the same way that if you want to find the internal shear at B, right, you would first treat it as a statics problem. You would solve for the reactions, and then you would cut the beam at B and use one side of that cut to find the internal shear moment there. If you use the left side of the cut, you need to know the reaction at A, right? If you use the right side of the cut, you need to know the reaction at C. Same idea. So here we have our reaction at A already noted. It's equal to 1, so that's just from our reaction influence line that we identified earlier. Okay. And then, so summing forces in Y and summing moments about B will demonstrate that the internal shear and moment are 0. But again, for these cases where the unit load is placed directly over support, you don't have to really demonstrate that. You can just say, we know it's going to be 0, that every other response will be 0, right? So then once we move that unit load off the support, that's where things get more interesting. So our reaction at A is 0.67. We already determined that, and I know that kind of looks like a 2, so I'm going to correct that to a 7. So from here, summing forces in Y, we would get the shear at B is equal to negative 0.33. And by the way, the units that are appropriate for influence lines are a little bit funky. So if you consider a unit load of 1 kip being applied, all right, you can use pounds if you prefer, but let's just say we are using kips. then the reactions that we found, right, will also be in terms of kips. And so the shear that we're finding, or the internal, or whatever response we're finding, right, is going to be a kip per unit kip. So this means that the internal shear at B, when the unit load is placed, oops, I wrote that in the wrong location, didn't I? Yeah, so sorry. This should be up here, where the unit load is at 10 feet. All right, so when the unit load is at 10 feet, all right, if it's 1 kip, then the shear would be 0.33 kips, right? But since we're using unit loads to generate that value, we're gonna say it's 0.33 kips per kip. So then when we go to the application stage of influence lines, let's say we want to apply 10 kips here, right? We know that the shear at B will then be negative 3.3 kips, okay? For moment, we just apply statics and we would get that the moment at B is equal to 3.33 kip feet per kip. All right, that would be the units for moment. And then moving that unit load another 10 feet, we've got our reaction at A is updated, right, to the value that's appropriate for this load case. Summing forces in Y, we would get the shear at B is negative 0.67 kips per kip. And the moment at B, we would find is going to be just the reaction at A times the moment arm of 20 feet. So 6.67 kip feet per kip. All right, so then the next placement of the unit load will take it off of our left side of the cut free body diagram, right? That's not a problem. We can still use the left side of that cut. I'm showing both sides now for demonstration purposes, but what we're actually doing in this case, right, so we've got the unit load now immediately to the right of the cut. As long as we're updating the reaction forces according to the location of that unit load, and in this case, we're just talking a hairline of a difference in location, right? So the reaction forces will be the same for these two cases. The difference between these two cases is the location of that unit load. So now we have the reaction of 0.33 on our left side, but we don't have that unit load. So that's going to update our internal shear. So our internal shear at B will be positive 0.33 as soon as that unit load moves off of immediately before the location of interest. The moment at B would be the same, all right? So that's not going to change. So 6.67. And then you can verify for yourself these values using the right side of the cut, right? So now you're using the reaction at C and you have the unit load present on that free body diagram. So I encourage you to check that on your own time. You should get the same values that we see up here, right? And so, of course, this is from the reaction at C influence line, right? All right, so continuing that, we have now the next location of the point load would be directly over the support at C, since we're doing 10-foot increments. So, of course, everything's going to be 0 other than the reaction at C. And then the last location is the free end. So we update, right, always update the reaction forces when you move the unit load, and then just apply statics and you'll get the correct results. So again, regardless of which side of the cut we are using for our free body diagram, we should obtain shear at B is negative 0.33 and moment at B is negative 6.67. All right, so now if we plot these values, let's see, I've got the red dots marking the supports. So we're going to plot, we'll call that 10 feet, and that would be B, which is the 20-foot mark. We'll say that's D. So we have negative 0.33 when the unit load is at 10 feet. When the unit load was at B, immediately before B, we got negative 0.67. And then immediately after B, it jumped to positive 0.33. And then we have 0 at C and negative 0.33 at D. So connecting those with straight line segments, it looks something like this. That's close enough. And so the notation we would show, right, would be, we'd say this negative 0.33 is equal to the shear at B when the unit load is at D. And for these guys, we'd say 0.33 is the shear at B, and then to demonstrate that the unit load is immediately after B, we would write B plus inside the brackets. So that's the notation that I use in this class. And then for immediately before B, we would say that's the shear at B when the unit load is at B minus. And so you'll notice, right, the slopes on either side of B are the same. All right, so we have continuous slope at the location of interest. For moment, if we plot those values, we have positive 3.33, and then we have 6.67 at B, 0 at C, and negative 6.67 at D. So plotting that looks something like this. That's close enough. All right, so this would be the moment at B when the unit load is at B. And this would be the moment at B when the unit load is at D. So here, the slope is not continuous, all right? So the slope changes at the location of interest. And these two observations will always be the case for shear and moment, respectively, okay? We'll talk about some more next time, but this is a good place to stop. We're also out of time, so any questions? All right. Well, good luck as you study. I will be here through my office hours today. If you have questions, feel free to stop by. I'm also going to be around this morning, so if my office hours don't work for you, but you have time this morning, you're welcome to stop by as well. I probably won't be here late in the day, though, so stop by early if you can, if you need to. And then, yeah, good luck. See you Monday.